Our ability to correlate what we learn in the classroom with the system of real life and to both qualify and verify those ideas via experimentation is a cornerstone of grasping information and achieving goals within science and math. For many learners and educators, reconfigurable equipment, like hobby and learning grade, for robots have become a natural medium to learn and evaluate. Robots are a very special category of machines, separated from others by their ability to be reused or reprogrammed. Because of this, the design, build, and operation of robots requires a wide variety of skills. Different types of robotics therefore become a way to delve into experiments with logical thinking, programming, and principles of math and physics, among other things. Some examples of these topics include the navigation of the robot and its impact of acceleration, deceleration, velocity, and displacement relationships for a more accurate and time-effective travel of the robot between 2 points in a 2D environment or 3D environment. The association between the wheelbase, the rotation of the motor, the wheel diameter, and the total distance covered by the robot as it steers through obstacles. Using levers, gears, kinematic chains, simple machines, and torque to force relationships when the robot is lifting objects with an arm. The load distribution and placement of the center of gravity on the robot when it's ascending or descending on a ramp.
Every robotics competition is different. Therefore, they all have their own unique playing field and format. The area where the robots compete is referred to as a playing field, and it's equipped with the needed parts and accessories for the field to be operational. In order to compete, participants must attempt to complete the task. The tasks vary from tournament to tournament. However, they usually require the robot to interact with the playing field and do pushing, pulling, lifting, or throwing action. Some competitions require robots to run entirely autonomously, while others allow teleop control. Autonomous means that the robot has to compete by itself without any human dependency. This requires a program to be written prior to the competition so the robot knows what actions to perform while in the playing field. Participants can also utilize a variety of sensors to grant the robot the ability to be aware of its surroundings. Some of the more popular sensors include the distance, light, and touch sensor. Teleop is the opposite of autonomous. It's when the robot is dependent on human input to perform an action. The most common way to compete using teleop is with the game controller. Generally, robotics competitions are organized into time-bound matches, which usually last 2 to 5 minutes.
Robot kits are fit for basic vehicle design. However, they're extremely limited because they cannot fit the specific requirements of competitive robotics. Because of their fixed connection patterns, their set sizes, and the weight of the robot because of the aluminum and steel parts used for the robot. This is where solid freeform fabrication can come into play and can address these limitations by making the robot lighter, task-oriented, and make the size more optimized towards the task. There are many manufacturers for robot kits, including Lego, Thames and Cosmos, Servosity, and Vex. Extrusion and channel-based robots by themselves can become very restrictive. On one hand, channels provide a distinct advantage by housing the motors and bevel gearbox arrangements within the channel, making the robot more compact. On the other hand, extrusions provide features for attaching small parts, and the channel and the extrusion can be used for rollers to build linear drives. While combining kits isn't very popular, it can make a difference in completing or not completing a task. This is because one kit may be more advantageous towards a specific task than another kit. Compatibility between each robot kit is important for using multiple kits within a single robot. Kits are rarely compatible with each other, seeing that adapters are solely based on the manufacturer. For example, a square hole channel cannot connect to a channel with a round hole pattern or an extrusion. Using a custom 3D adapter, you can easily connect parts from different kits. As shown in the picture, you can connect an extrusion to a channel using the adapter. As you can see in the picture, you can connect the extrusion to the channel in many different ways.
In a channel-based kit, end effectors can be kind of bulky and move the center of gravity, making the robot more likely to tip over. However, a 3D printed part is tailored to specific needs. It aligns the center of gravity because of its reduced weight and has a better grip due to its customized shape. Another example, as you can see in the picture, are the two hubs and battery, which are used to control and power the robot, and are placed on the side of the robot, which causes the wires to be extremely disorganized and the load distribution to be asymmetric. A solution to this problem that we came up with was that we placed the hubs and battery below the ramp. But we couldn't do this since the tools needed to fasten the hub and battery would restrict the use of the ramp. So a final solution that we came up with was using a 3D printed cartridge-like housing that had better organization and reduced the tension of the wires by using the concept of mechanical isolation. Another part of the 3D printed housing is that there are built-in shock absorbers. Another example is the camera we use during autonomous modes mount. It was built with a channel-based kit, which exceeded our height requirement of 2 inches. We also had to tape it from the top to hold it in place. The tape was extremely unreliable and let the camera move around a lot. The solution we came up with for this was to use a 3D printed mount with specific alignment and exact height.
Next thing we used 3D printing for was suspension systems. When the robot travels on uneven terrain or bumps into objects, it can cause damage to the onboard electronics. Suspensions can dampen the bumps that the electronics experience. However, the base kit doesn't provide any fasteners or dampening mechanisms. 3D printing can be used to create these custom suspensions. We created a linear suspension system that has a spring enclosed in 2 cylinders, as shown in Figure 1. Due to the suspension system needing more degrees of freedom to move to function efficiently, the cylinders were removed and the thickness of the spring was increased to accommodate for weight, as shown in Figure 2. It also has mounting holes on either side to attach to the components. Another thing we used 3D printing for was the creation of custom bevel gears. The bevel gears provided in the base kit have small teeth engagement, which cause them to frequently slip. We used 3D printing to create bevel gears with deeper teeth, which eliminated the gear slip. With 3D printing, custom gear sizes can also be created, which would allow teams to have any gear ratio they need. Based on what we previously saw, 3D printing has many benefits compared to using stock parts. It allows for the creation of custom parts that are not available on the market. For example, custom adapters can be created to attach parts not commonly able to connect to each other. It is also a faster alternative compared to ordering parts online. For example, ordering a part could take up to 3 days to arrive. However, 3D printing will only take a few hours to create a part. 3D printed parts are also lighter than metal parts since they are made from plastic. Due to this, they can lessen the weight and load on the robots. This is useful because many competitions have a robot weight limit. Printing parts is also cost-effective compared to buying stock parts. On the market, bevel gears can cost up to $15, but with 3D printing, the cost would be decreased to $1 to $2. Thank you for your attention. We are open for any questions you may have.